In previous lectures, we talked about population models for closed populations that only experience changes due to births and deaths. Each time we looked at one of those models, though, it was for a single population. So in this lecture, what we're going to do is bring in two populations, which are closed, so there's no immigration nor hunting. And these two populations have a predator-prey relationship. So in particular, suppose we have foxes eating rabbits. We'll model the population of foxes over time as f of t, and the population of rabbits over time as r of t. So that's the number of foxes and the number of rabbits at some time t, respectively. We're going to build these models up, and we're only going to assume a few things. So to start with, what we'll say is that in the absence of foxes, the predator, the rabbits will grow at a rate proportional to their current size. However, with the introduction of foxes to the environment, the rabbits decline at a rate proportional to the interactions that take place between the rabbits and foxes. We'll go through the details of what that means in a second. Similarly, for the foxes, if there are no rabbits, then the fox population will decline at a rate proportional to their current size. So we'll get some sort of decay. However, with rabbits in the environment, the foxes will grow at a rate proportional to the interactions that take place between the two species. So with both rabbits and foxes present in this ecosystem, the number of interactions they have will decrease the rabbit population but increase the fox population. Now, when I set up this model, I thought of foxes and rabbits, just a traditional predator-prey relationship, but perhaps I should have chosen two different species because we're going to assume no breeding seasons, which I think foxes might actually have. So while we could set this up discretely using like difference equations or something like that, we're going to do a continuous model. So we imagine that the fox and rabbit populations are changing continuously throughout the year. We don't have one time a year when the foxes give birth or something like that. What we're going to do is take these first four descriptions and put together a pair of differential equations. One line will tell us how the rabbits change, and the other line will tell us how the foxes change. We'll have a pair of differential equations which we will not try to write down explicit functions for. What we're going to do is take our differential equations and visualize them numerically and analyze them qualitatively. We'll give a good picture of what will happen to the rabbits and foxes over time, and we may be able to give precise measurements for their long-term behavior. In the next lecture, we might change one or two of these hypotheses and see what that does to the model. Okay, let's look at what happens to the population of rabbits over time. So dr dt is the rate of change of the rabbit population with respect to time. We have two conditions here for the rabbits. One tells us how they grow and the other one tells us how they decline. Let's call the first one number 1 and the second one number 2. Hypothesis number 1 tells us if there are no foxes, then dr dt is proportional to the current number of rabbits, the current population. So we can say dr dt is equal to a times r. Here, a is just a positive parameter. And we recognize that that's our growth number that's depending on the number of births and deaths, but we're assuming here that the rabbits are growing. So births minus deaths is some positive constant number a. Now let's introduce foxes to this environment. We have here two conditions on how the rate of change of the rabbit population with respect to time should vary proportional to two other measurements. The rabbit population is a quantity that's going to vary as a sum of proportions. This is sometimes called superposition. It's a superposition of terms. We add them together. So to give the effect that the interactions between rabbits and foxes has on this rabbit population, what we're going to do is take our equation that we came up with after reading hypothesis number 1. So that says dr dt is AR. And we're going to subtract a term, so it's going to be minus some term that measures how often the rabbits and foxes are likely to interact. And what we do is we take the product of the rabbits with the foxes, Because that tells us every possible way that we could have a fox and a rabbit interact. If we have 10 rabbits and 5 foxes, there are 50 ways to pair those up to have an interaction. So that's the idea with this product, is the more rabbits and the more foxes you have, the product gets even larger because you're more likely to have them interact with each other. If you have very small populations, they might not see each other very often, so that product is a low number. You don't have that much interaction. What we're going to do is have b be a parameter in front of this product. So this parameter b here, which is going to be a positive number, is telling us how these interactions have an effect on the rabbit population. So overall, we have two parameters, a and b here, and they're both positive, so we have that subtraction to indicate that the second term brings the rabbit population down. Now let's look at df dt. This is going to be the rate of change of the population of foxes with respect to time. Let's number these hypotheses 3 and 4. We'll say that 1 and 2 went with the rabbit population. So what does hypothesis 3 tell us? It's just like hypothesis 1, except here the foxes are declining. So we'll say that df dt equals negative c times f, where c is some positive parameter. Again, that's like a birth versus death quantity for this fox population, except here the foxes are declining in the absence of food. Once again, we have two hypotheses though. We're going to take their superposition, so we'll add them together. If there are rabbits, then the fox population will grow. So how we'll take the differential equation that we've already written down and change it is we'll say df dt is going to be negative cf plus d times rf, where once again this latter term is measuring the effect that the total amount of possible interactions has on the fox population. It's of course positive because the more interactions we have, the more the foxes can eat rabbits, so this is going to increase their population. With this equation, we pick up two more parameters, c and d, and the way I've set this up with the signs, both of those are also positive. This pair of equations can be viewed as a compartmental model, where we view the populations rabbits and foxes as two quantities, and we want to model what's coming in and what's going out. So typically we do a visual schematic for that. We'll have the rabbits and the foxes as two boxes. So let's say this top box represents the rabbit population, and the bottom box represents the population of foxes. Now we diagram what's coming into the population versus what's going out. So for the rabbit population, we increase due to the a times r term, whereas we decrease due to the interactions the rabbits have with the foxes. For the fox population, we increase due to the interaction with the rabbits, their food. But the fox population has a tendency to die off, say, in the absence of rabbits. What we want to do is take these two populations and couple them together. I wrote down both of those equations separately, but they can't be viewed separately. These two equations must be coupled together. And the reason why is there's some circular interaction happening between these two equations. dr dt is going to change the r population, which means if you look at how the fox population changes, that's going to give the foxes more food, so the fox population will also change, which means that the second term back here in the r equation will also change, changing the r equation again, changing the foxes, changing the rabbits, etc. You can't use just the first equation to study either population because there are two terms, two functions, r and f. Each are changing, so you need to have each of their descriptions for how they change over time. So we must view these together, we can't separate them. So this pair of equations taken together is what we call a system of first-order differential equations. And this pair is very famous. It has a name. It's called the Lotka-Volterra equations. Lotka and Volterra were two mathematicians. They both discovered this set independently, so they share their names with this system of equations. In particular, Volterra was a mathematician whose future son-in-law wrote him with some scenario that would be modeled by this system. So the son-in-law, or aspiring son-in-law really, was like, hey, can you help me out with the system? And then he married Volterra's daughter and joined the family. As I mentioned earlier, we're not going to write down explicit functions r and f that satisfy these equations. So what I mean by that, well, if I cross out everything except the dr dt equals ar term, if I'm just looking at the rabbits and I've wiped out the foxes, we could solve that. That would have an exponential solution. But now let's reintroduce foxes to this ecosystem. And we can't easily write down two functions r and f which make these simultaneously true. We're not even going to try. However, we can try to find special values of r and f which never change over time. So if we can find particular values for the rabbit population and the fox population so that when both are simultaneously plugged into these equations, the derivatives both equal 0, then we would say the rabbit population will never change, the fox population will never change, so the rabbits won't change because the foxes aren't changing, and the foxes won't change because the rabbits aren't changing. Nothing is changing. So these are special population values that result in no change over time. In other words, both derivatives are always 0. To find those equilibrium solutions, what we do is just set the left-hand sides equal to 0, or rather I take the left-hand sides and replace them with 0. We get a system of equations. So now the derivatives r prime and f prime are 0. And on the right-hand side, we're going to just do some algebra to try to figure out what r has to be and what f has to be simultaneously to make both of these equations true. This isn't too hard because on the first line we can factor out an r and write this as r times a minus bf. And similarly on the second line I can factor out an f and write this as f times negative c plus dr. So one immediate solution is r is 0 and f is 0, which we can write as an ordered pair. We'll say r comma f equals 0 comma 0. That shouldn't be surprising because that's like saying if you don't have any rabbits or foxes in your house, you never will, just based on births and deaths. So this is an equilibrium solution. If, however, you do have rabbits, then when we look at that first line, if rabbits are non-zero, this first line is only 0 if f equals a over b. A and b are positive, so now f is non-zero. The second line would tell us that if f is not 0, then rabbits must be c over d. Okay, so the second equilibrium solution, written as an ordered pair, is rf equals a over b. Sorry, actually I got that backwards. C over d, comma, a over b. So we have a total of 2 equilibrium solutions. The first one is trivial. We're not interested in an ecosystem where foxes eat rabbits if there are no foxes and there are no rabbits. So the second one is more interesting. So this is some positive number of rabbits and some positive number of foxes, and if we observe the populations at those levels, then we would never expect them to change. Rabbits will neither grow nor decay, and same story with foxes. That's a really special scenario where both populations are constant. What happens if we have any other combination of population values? Since we're not going to explicitly solve this pair of equations to get functions r and f, we need a way to do this numerically. So we're going to do this in MATLAB, and this is the beginning of a script that I'm going to build off of. So here are the parameters A, B, C, and D. I've given you values here that we'll stick with for most of this lecture. I don't think we'll change these too much. Then down here, I've set up a calculation with the ODE45 command in MATLAB. That's a pretty traditional command to use to solve this kind of differential equation. What we're going to get out of this command is two sets of information. T is a time vector. P is a matrix with two columns where the first column is the rabbit population. Each entry in that matches the time entry. So the first entry will be the rabbit population at the first time. The second entry will be the rabbit population at the second time in the T vector. And ditto for the fox population, that's in the second column of P. So P is a matrix encoding both the rabbits and the foxes, which means that we can plot them. We'll do two plots. One will be each population over time. In other words, we'll plot R with respect to T and F with respect to T, and we'll put them on the same plot. So that's going to give us some interesting shapes that we can analyze. And then the second plot will be foxes versus rabbits. So we'll plot those two vectors. We'll plot R like the vector of independent measurements and F like the vector of dependent measurements. So we'll treat foxes like Y and rabbits like X, which is going to give us a curve. It's going to take shape showing how those populations change with respect to each other. So this will be like a curve parametrized by time. It will be R of T, comma, F of T. We'll be able to describe that better when we actually have the plot in front of us. Down here at the bottom, we'll make a little adjustment to this later, but in general, I don't want you to worry too much about this. This is called a nested subfunction, and what it's doing is setting up this ODE45 command to run. So the output we get from this function, what I'm calling dp here, is encoding both r prime and f prime. Had to give that function a name and feed into it pieces of information. This line right here, dp1, this is encoding the r prime equation. So you can see a times the first population minus b times the product of the two populations. The second line is encoding the f prime equation. So that's minus c times f plus d times the product. And then dp is going to couple those two together. Going back to the ODE45 command now, we then tell ODE45 this is the equation we want you to solve. So this is all just a MATLAB construction. MATLAB gets to this, comes down to the bottom here and says, okay, these are the equations I'm going to work with. The next two pieces of information actually are important for us to be able to adjust. So this is the time span. The way we've set this up, at 0 is less than or equal to t is less than or equal to 200. But that's something you can adjust. And then this vector is the vector of initial conditions. So this is telling us that the initial rabbit population, just in this piece of code, is 100. And then the second entry tells us that the initial fox population is 60. Okay, so I'm going to take this code now and open it in MATLAB Online, and we'll start to adjust it. I'll make a lot of changes, but all I really want you to be able to do is adjust the time span, adjust the initial populations, adjust the parameters if you want, and we can dress up the plots too. We can label our axes and give them titles and things like that. Later, when we adjust the model, we might come down here and change these equations a little bit, but this isn't something down here that you're expected to change every time you tweak a parameter or something like that. This is where the equations are stored, and they've been written in such a way that MATLAB recognizes A, B, C, and D as the parameters that we name up here at the top of the code. Okay, so let me copy this into MATLAB. Okay, I've cut off the top of MATLAB Online to really have the largest window I can for my script file since we have so much going on here. But this is copying over what was on the screen. So we have our parameters, the ODE45 solver all set up with this nested subfunction, and then I've got two plots which are going to appear. Except that the first plot will appear, and then it will possibly plot this on top of that because of the hold on. What I'm going to do is add the word figure above both of my plots. That's going to cause MATLAB to create a new figure window for each. So this is going to open a new figure window, and it's going to do that both times. In other words, we're going to get two distinct plots. Okay, let me go ahead and save this, and then I'm going to run it so that we can see what the plots look like. Let's start with figure 1. Okay, figure 1 that we're looking at right now was the population of rabbits and foxes both plotted over time. To make that clear, let me do X label is time, and I don't really have a unit for time here. Let's just say months. This is a continual model, but we'll say this is after 200 months have gone by or something like that. And then for Y label, we'll do populations. And then title, this is fox and rabbit populations over time. There, a lot to type. Okay, I just ran that, and then I had an experience where a bunch of figure windows popped up because I'm going to get new figure windows every time I run this. So let's do close, clear, CLC at the top just so we don't get like 50 figure windows by the end of this. Okay, so the black curve up here with the higher spikes, this is the rabbit population. And the red curve down here, this is the fox population over time. Let me actually add a legend just so that's clear. So we'll do the first curve I plotted was the rabbits. The second curve was the foxes. Okay, I ended up closing the second figure. So here we're just looking at the first figure. Okay, this is where we started. And actually I don't want to keep dealing with the second figure window for now. So let me suppress this code and we'll just have the first one. We can see what would happen if we did something like changed the initial populations. If we wanted to do that, it would be this final entry in that ODE45 command. So we're starting with 100 rabbits and 60 foxes. What happens if we start with 400 rabbits? Okay, you can see it looks a little different here. Qualitatively, it's kind of similar with oscillations for both populations. But that's one thing that you can investigate is how the initial population changes it. Let me go back to the spikes that we were looking at. Okay, I like this one. It's very dramatic. So what happens? Well, both populations oscillate over time, but particularly if you look down here at the fox population, you can see it's not sinusoidal, for example. It's got some shape to it. It looks to me like the period for both populations is the same. So if you compare the gap between the spikes and the dips in the rabbit population, seems like we have the same period, but they're not rising and falling at exactly the same moments. So in particular, when we started, apparently this was a small number of rabbits for this ecosystem. Since it was a small number of rabbits, the fox population declined and it kept declining. During that period, as the predator population was going down, the rabbits really multiplied. So the rabbit population spiked first before the fox population ends up having its first spike on this plot. What happens is at this point, there's a ton of food. There's going to be more interactions between the foxes and rabbits, which means the fox population starts to turn around. They have a lot of food to eat, so their population starts going up. But then, as the predators go up, those interactions end up hurting the rabbits, so they go down. That happens before the fox population goes down, then they don't have enough food, and the cycle continues. So you can see we get this cyclical behavior where an increase in food leads to a slightly delayed increase in predators, which leads to a decline in the food, which then leads to a decline in the predators. Again, you can take this code and see what would happen if it was 200 rabbits and how about 20 foxes? Okay, very similar shapes, they get really close down here. Versus when we had something like 500 rabbits. Okay, that was not that dramatic of a change. How about 40 foxes? I don't know, I'm just guessing right now. Okay, there you can see sort of different. And in this case, you don't see quite as much shape in the oscillations as you do in the first case. You could see what happens if you have more foxes than rabbits. Okay, so in this scenario, I start with 100 rabbits and 400 foxes. That's so many predators for a fairly small food supply relative to the number of predators. So you can see the foxes just immediately die off. They go almost all the way down to 0, but not quite. The fact that there are so few predators then allows the rabbits to flourish. So they go up from 100 at the start to, what is this, about 5,500 or something like that, at which point the foxes have something to eat. And you can see here the oscillations are like really shark fin shaped or something like that. So you can play with this. Qualitatively, it's the same behavior each time. We're getting oscillations with the same period, but not exactly in sync. Okay, let's go back to where we started. In this scenario, we have 100 rabbits and 60 foxes. Again, those aren't particularly special numbers, but that's just what we'll stick with for a minute. Let me now actually close this figure window. I'm just going to put comment symbols in front of all of these lines, and we will uncomment our second plot. Let me run this. The way we've plotted this, rabbits are on the horizontal axis, foxes are on the vertical axis, and what's driving the motion around and around here is the passage of time. In fact, if you want to, you could change this plot command to comment. It's going to make it like a comet. Okay, so there you can see how that curve takes shape. So apparently the oscillation in this particular picture is happening in a counterclockwise fashion. That should make sense because the idea is as the rabbits increase, the foxes start to increase. So this kind of motion from bottom left to top right along the lower half of this, as the rabbits go up, the foxes go up, but then once there are this many foxes, the rabbits start to decline. Foxes are actually still going up, but now there's not a lot of food. So now the foxes are going down, rabbits are still going down. But then once the predators get really low, the rabbits start to go up. And you can see that cyclical behavior again. I'm going to do something here to my code. This is not something I expect students to know how to do. But I'm putting here a line that's going to change the tolerance of the OD45 solver. That's going to make this curve a little bit more smooth because actually we shouldn't have distinct curves every time we go around. It really should just be one curve. So I'm going to add this option at the end of the OD45 command. Now that I've done this, it doesn't need to be done again. So if I run this, and I'm going to change it back to just plot. You can see it's really just one curve, so it's not slightly different every time, it's the same curve. Let's plot our equilibrium point in the middle of that. So I'm going to do hold on, and then scatter. The equilibrium value for rabbits was C over D, and for foxes it was A over B. Okay, you can see that's right there. So if rabbits and foxes were at that value, they would stay at that value forever. In fact, we might as well just try that as an initial population value. Let's maybe look at that first figure too. Okay, here's our second plot. No surprise. We started at the equilibrium solution, so we stayed there forever. That's why we just have a dot. And in the first plot, it doesn't look great because 50 is down here at the very bottom, but what we get is just horizontal lines for the foxes and rabbits because they're not going to oscillate over time. They're constant. Okay, what was C over D? 400 and A over B, 50. Okay, so 450 would do that. Let's make it 440 and 40. Okay, there's not that much of an interesting thing here. So let me do something. I just want to illustrate something kind of neat, and that is that the plots that we'll see in the second plot are going to take a special form as I change the initial conditions. So we're going to get rid of the first plot again. Sorry to be jumping back and forth, but basically what I'm going to do now is just have the hold on. I'm going to plot the F versus R curve for different values of the initial condition. So let's start with, how about 100 and 10 or 20. Okay, now if I adjust this, it should stay on the same plot because of the hold on command, and also I got rid of that close. So let's do, how about I just adjust the rabbit? So 220, 320, 420. Okay, let me adjust these. How about 30, 40, 50 is actually the dot. Let's go up to 60. Let me go up to 450. I'm just kind of doing populations near, about 410 and 52. That should be really near the dot. Yeah, there it is, right around that dot. About 56 and 415. I don't know. There we go. Okay, so you can see we get these concentric shapes here. It's kind of like seashell shaped or something. They're not perfect circles or ellipses or anything like that. They get a little bit more elliptical as you get closer and closer to that equilibrium point, whereas out here, they're much more exaggerated. In fact, let's do something that's really, really exaggerated. Let's do 2 and 2. Okay, so there you can really see like a seashell shape. Let me also do 2 and 4. Okay, and 2 and 6. Just trying to fill in a little bit. Okay, so when we do our foxes versus rabbit populations plot, you can see that we get these concentric orbits. Which one you're on just depends on the starting populations. The closer you are to the equilibrium values, the closer you are to being kind of elliptical and right around here. If you're very far from those equilibrium values, then you get this more dramatic shape. But all of these population curves tell us that over time, we just expect that oscillatory behavior where the populations spike and dip slightly out of sync. What's the long-term behavior then? It's just this oscillation. Neither population is going to grow out of control nor go extinct. Whatever the initial conditions are, we expect to just follow that course for all time. All right, I apologize if I was kind of jumping all over the place with my MATLAB initial conditions there, but hopefully that gave you a good picture of what the Lotka-Volterra equations that we have set up predict for the fox and rabbit populations over time. It's natural to wonder if we could have done any of that by hand, and you can actually do quite a bit. Let me just give you a demonstration of one aspect of what we saw that we could generate without MATLAB. So in particular, if you think of the second picture that we were looking at, that was foxes versus rabbits. The graph that we numerically generated in MATLAB showed one equilibrium point somewhere in this quadrant and then orbits around it. Let's see if we could work out that counterclockwise motion by hand. So in particular, if we have some shape, like the shape we were looking at, if I could view, say, this upper part as a function f of r, foxes depending on rabbits, then we can see the shape of that if we could perhaps picture what tangent lines to this curve would look like. So if I could understand what tangent lines look like, I might be able to figure out the actual shape itself, or something close. By the chain rule for differentiation, we can express df dr in terms of df dt and dr dt, which are the expressions that we already have in our Lotka-Volterra model. So df dr, the rate of change of foxes with respect to rabbits, can be solved for by taking df dt, the expression we have for that, and dividing it by dr dt. That's from the chain rule. We actually have both of those derivatives. Those are the two lines in our Lotka-Volterra model. So the first one is the fox line. So that's going to be negative CF plus DRF. And then the denominator is the first line in our set of ODEs. So that's going to be AR minus BRF. Let's do the obvious thing and factor f out of the numerator and r out of the denominator. So we'll have f over r, and then we'll be left with negative c plus dr in the numerator, and in the denominator, A minus BF. Recall that the equilibrium steady state that we identified happened when R equaled C over D and F equaled A over B, which are the kind of terms that we see in this numerator and denominator. So what I would do next is actually factor, let's say, D out of the numerator and negative B out of the denominator. So this almost looks like df, like a derivative, but that's d, the parameter. In fact, let me just write this as one big fraction so that it's a little less confusing. It looks a little bit like a derivative. Okay, in the numerator, we're then left with r minus c over d. And in the denominator, we're left with f minus a over b. And now this is a nice thing to see because r and f are being compared to their steady state values. So let's plot those steady state values, and then we'll figure out what df dr would have to look like in different zones in this first quadrant. Okay, so let's say that c over d is here on the rabbit axis. So this is the vertical line r equals c over d. And let's say a over b is here on the fox axis. So this is the horizontal line f equals a over b. Where they intersect is our steady state solution. Okay, what happens if we're up here in the top right quadrant? That means r is greater than c over d because we're to the right of that line, and f is greater than a over b because we're above the horizontal line. So if we look at our expression here, both of these terms written in factored form are positive. D, F, B, and R are all positive. We have one negative sign down here, so we have a positive number divided by a negative number. So overall, this would be a negative slope. In other words, if we were looking at a solution curve, f plotted as a function of r, negative slope would tell us our tangent lines are going to be angled like that. If I rotate over here now to the top left, f is still greater than a over b, but r is now less than c over d. So we've switched the sign of the numerator. That means we're going to have negative over negative. Viewed as f as a function of r, would have a positive derivative in that quadrant. That indicates that your tangent lines would be angled up like that. And if we come down to the bottom left, both r and f are less than their equilibrium solutions. So we have negative over negative times negative. So that's going to be negative again. And then cross over the line r equals c over d and will be net positive. You can then also fill in the behavior on the lines. So when r is c over d, it's flat. When f is a over b, it's undefined. We can reason from the rest of this picture that that's going to mean vertical. This doesn't tell us that our orbits are closed loops. They could be spirals. So we do have a sort of circular or elliptical or round shape here, but that doesn't mean that from this picture we can leap to the conclusion that they're going to be closed orbits. But we do get a sense of shape. To fill in the direction of motion, we can realize that in the absence of foxes, rabbits increase. So we're traveling this way along the x-axis. And similarly, in the absence of rabbits, foxes decrease. So we're traveling this way along the fox axis. It doesn't make sense to say with one rabbit, the fox population is going to reverse its course. Everything needs to line up kind of consistently here. So if we scoot that sense of downward motion over to the right, kind of piece it together, we get consistency if we draw our directions of motion going in the counterclockwise direction. There's more you can do here, but I just wanted to give you a glimpse of the kind of analysis that you can do by hand if you don't have MATLAB. All right, at this point, we have created a model. We defined the variables, specified the parameters, we wrote down the model, and we implemented it in MATLAB. Then we were able to analyze the long-term behavior of the solutions that MATLAB was giving us graphically. So now the question is, are we done with this scenario? Or are there any changes that you might like to make to this model? In the next lecture, I will suggest a change. But before you watch that, go ahead and think over what you might do differently. So were there any assumptions that we placed on the rabbit and fox populations that you would adjust? Once you've had a chance to think that over, go ahead and watch the sequel to this lecture to see one possible change.